Hello, my name is Christine Lindstrom, and I am a physics education researcher in the School of Physics at UNSW Sydney. At UNSW, I lead the research arm of the group Physics Education Research for Evidence-Centered Teaching, or PERFECT for short. In this talk, I will share with you a pedagogical tool that is as powerful as it is simple. Let me introduce you to wonder questions and how they can be used for engaging, motivating, and illuminating both students as well as teachers. Wonder Questions is a simple, flexible, and pedagogically powerful tool that quickly became and has remained a favorite of mine. First, a note on terminology. I speak of wonder questions in the singular when referring to the pedagogical tool, and in the plural when referring to the actual wonder questions generated by students. I developed Wonder Questions as a pedagogical tool in 2012 when I first started teaching physics to pre-service science teachers in Norway. Since then, they've been used successfully by several of my former students as they have become school teachers themselves, and I have gone on to using Wonder Questions in more traditional physics courses now at UNSW Sydney. So, what is this pedagogical tool? Well, Wonder Questions is a formative assessment task that requires students to produce a question rather than an answer. It can be posed in the following way. Write a wonder question. A wonder question is something you wonder about after having done the pre-work that is related to it, but not necessarily covered by it. To make the most of Wonder Questions, I found a flipped classroom structure ideal. Students receive the initial exposure to course material before class, which gives them time to actively reflect on the new material they have been exposed to and try to connect it with prior knowledge before they engage in a formative pre-lecture quiz. And this is where the Wonder Question task is included. This encourages a more active processing of new material, which is associated with better encoding of new information, leading to better retention of new knowledge. The teacher subsequently evaluates the results of the quiz in preparation for class. In this regard, Wonder Questions provide valuable insights into what students know, what they're on the cusp of understanding, how they reflect on new information, faulty attempts at integration, and what they're curious about. This insight, including explicit use of Wonder Questions, can then be integrated into the design of a student active class, which typically includes mini lectures on topics students found particularly challenging in the pre-work, formative peer instruction questions for students to test their understanding and give the lecturer valuable feedback on their progress, and possibly other small group activities. Students' Wonder Questions come in a variety of shapes and sizes, and I have found it useful to categorize them into 4 types. Note that these types are not mutually exclusive. The categorization is merely a helpful aid in guiding how to use them. There's type 1, which refers to simple questions that show correct understanding. There's type 2, which refer to wonder questions that show students' connections with real world. There's questions that go beyond course material. And there are wonder questions that show student misconceptions. Each of these types reveals something valuable about student interaction with the material and has a particular set of pedagogical uses. I'm going to go through these 4 types now, including examples and pedagogical uses. So the first type is correct understanding. And these are questions where students wonder whether they have understood something correctly in a way that's not explicitly stated in the course material. The pedagogical uses of this type of wonder question is that you can intersperse mini lectures with these questions to paraphrase material in students' own words, possibly adding a confirmation or a small elaboration. Or they can be used as true-false peer instruction questions to check if the rest of the class has understood the material sufficiently well to recognize if this is a statement with a correct understanding shown. Couple of examples. Student asked, if a compass is able to freely move in all directions, including up and down, would a compass on the South Pole then point upwards? So this wonder question was simply inserted into a mini lecture on magnetism with a simple affirmation. Another one. Is it correct that if one weighs an object above and underwater and the difference is 1 kilogram, then the water that corresponds to the volume of the object weighs 1 kilogram, regardless of what material the object is made of? This wonder question made for a very good yes-no peer instruction question to check if my students had understood Archimedes' principle. Wonder question type 2, real-world connections. These are questions that are largely covered by or understandable based on course content, but generally connected to real-world examples that may not have been mentioned in the pre-work material. Pedagogical uses of this type of wonder question are the following. They provide opportunities during mini lectures to relate the course content to real-world examples, which is generally quite motivating to students so they see the applications of, well, physics in this case. They can also be used to highlight limitations of simplifications presented in the course material that may not have been brought in the pre-work. And lastly, they can help structure the coverage of material around what students are motivated to learn about. So let's look at a couple of examples. Lightning strikes are a form of electric discharge. Given that air does not conduct electricity, why do we see bolts of lightning to the ground? Now, this wonder question was inserted into a mini lecture with the following elaboration. Air is usually an insulator, meaning that it doesn't conduct electricity, but it can conduct electricity if the potential difference is sufficiently large, around 3 million volts per meter. The extremely strong E field then rips electrons off the atoms, so the atoms become ionized and therefore conducting. The lightning then follows this ionized channel and has an average current of a whopping 40,000 amperes. Simple one. Where do double rainbows come from? Now, this was asked me by 2 pre-service science teachers, and it turned out to be such a good question that I actually restructured my whole lecture around it. So I restructured the pre-existing class material on light to build an answer to this question over an entire 3-hour class. For each stage that we went through, mini lectures and activities help students learn the underlying principles of fusion, transparency, refraction and reflection, lenses, and in the end, light detection. Wonder question type 3, beyond course content. These are wonder questions that require content understanding that go well beyond the course material. Pedagogical uses of this type includes that they offer an excellent opportunity to demarcate the course boundaries and show how the content connects with future or with other courses the students might be doing. Questions that are similar to authentic research questions may actually be suitable for class research projects. But with this type of questions, the teacher should not feel obligated to fully answer such questions, and they may just end up pointing out that there are many questions still unanswered in physics and in science And this is what researchers are working on at the moment. Examples of this type of wonder question are the following. Since electrons are negatively charged and protons are positively charged and neutrons have no charge, why aren't the electrons attracted to the protons, resulting in a big atom lump? Now, this wonder question was inserted into a mini lecture indicating its connection with quantum mechanics. When Rutherford in 1911 proposed his solar system model of the atom, where electrons orbit a positive nucleus, his fellow physicists were wondering exactly the same thing as was posed in this wonder question. And actually, this is what gave rise to the field of quantum mechanics. However, we will not properly cover the answer in our physics courses, which was in pre-service science teacher education, where quantum mechanics was not covered. Another example. Will we really be able to overcome the inevitable future of climate change and the detrimental impacts it's having on our planet, considering it's already caused so much damage? This wonder question, along with several other excellent ones, was posed to the CEO of Planet Ark, Paul Klemenko, whom I was able to interview using my students' important queries into climate change. Last type of wonder question, type 4, misconceptions. These are merely wonder questions that reveal misconceptions that students have. Pedagogical uses of this type is that such questions give the teacher authentic material to address misconceptions in class. You actually know that students, maybe just one, but at least one, has this misconception in your class. Questions that students should be able to answer may be used for peer instruction questions, either directly or modified. They can be used in group problem-solving sessions, or maybe even for laboratory experiments. And lastly, the teacher can also choose to select one or more wonder questions to give as an extra challenge to a subset of students, such as gifted and talented students in middle school or high school, for example. Does light accelerate differently through vacuum glass and water? And the simple misconception here was that light accelerates. And here's another two. I don't understand why kilowatt hours is a unit for energy when it's used to calculate power. And how can the unit of watt be 1 joule per second and still have the unit kilowatt hour, which also says something about the time? There's clearly some serious misunderstanding going on here. So based on the pre-work, students should have understood units at the stage where they ask these questions. So I jointly responded to these two questions by requiring the students in class to work in groups of 3 on how you would answer these student questions. And so we've made it to the end. The pedagogical power of wonder questions lies in the ability to engage, motivate, and illuminate both students and teachers in the following ways. Wonder questions as a pedagogical tool. Engage students and teachers by modeling scientist behavior, requiring students to actively process course material to ask good questions, and similarly requiring teachers to reprocess the material in response to the wonder questions. Wonder questions also motivate students to approach material in a more personalized and curious way, and motivate teachers to refresh, restructure, and tailor material for their particular class. And lastly, they illuminate the material from different angles for the students and clarify students' prior knowledge, understanding of, and motivations for the material for the teacher. Wonder questions has become one of my very favorite pedagogical tools, not just because it's simple, not just because of its ability to engage, motivate, and illuminate, but perhaps most of all, because it makes teaching even more enjoyable. Thank you.